Welcome to the finals in my series of talks about ASIN and AreaDetector. Today we're going to be talking about how to write AreaDetector plugins. Yesterday we did drivers. Drivers are the code that talk to a particular detector, and plugins are the code that are detector independent, that do sort of the real-time processing on the ND arrays after they're collected by a particular detector or camera. And the outline of today is similar to yesterday. What I'm going to do is just sort of have just a few slides that describe general principles about how to go about writing plugins, and then actually look at the code for a few specific plugins. And then for the hands-on part, we've got a plugin that I actually wrote yesterday after the class. So it's hot off the press. But I think you can get the idea that you can actually write a plugin that does something useful fairly quickly. It's not that much work. If you feel that there's a need to write a new plugin because you need to do some kind of processing on arrays that isn't handled by the existing set of plugins, then as with a detector driver, you should look at the existing plugins to figure out which one probably is closest to what you want to do and use that as a model. And this is the list of the existing plugins that are included in AD Core. There's also the FFmpeg plugin that's included that's in its own separate module. And I've categorized these by a few of the properties, the characteristics of these plugins. The first is it the type of plugin that generates new ND arrays? Or does it is it both a consumer and producer of ND arrays, or is it just a consumer? And what, if any, limitations that plugin has in terms of what kind of arrays it can handle. And in general, I think when you're writing a driver, you have a specific task. You're trying to write something that's specifically targeted to that detector. Of course, you should try to generalize on the features that you support. So, not just the features you need tomorrow, but try to, as time permits, implement as many of the features of the camera as you can. With plugins, the goal should be to try to be general, because although you may be writing it to work with a specific camera, hopefully other people will find it useful and maybe be working on it with other kinds of cameras or chaining it into a plugin chain. So you want to make it so that it works with as many data types and dimensionality of the data as possible. So first, there's the region of interest plugin. These are in no particular order here. The region of interest plugin does generate new arrays. It generates arrays that are subsets of the input data, possibly transformed in their order and their binning and the order of the array in a particular dimension, and the binning and the data type. And it really doesn't have any limitations on the input arrays. It treats color a little bit specially to try to make it simpler when you're switching from one color model to another, but it can handle any type of input array. The statistics plugin is only a consumer of ND arrays, so it doesn't generate new ones. It's written to be as general as I could make it, but some of the functions there are limited to two-dimensional mono data. So the simple statistics like the minimum and the maximum and the mean and the pixel location of those are general, but the the centroid and the profiles are limited to two-dimensional mono images, not color and not n-dimensional. The processing plugin generates new arrays, and it also doesn't have any limitations on the input array dimensions or data types. The transform plugin, this is the one that does rotations and mirror operations, generates new arrays, and it's limited to 2D mono and color only. The standard arrays plugin does not generate new ND arrays. It puts the data into one-dimensional arrays, the kind that Epix knows about with a waveform record, and it doesn't have limitations. And it can convert any input, any ND array data type to any Epix 1D array data type. There's the overlay plugin, does generate new arrays. It's limited to 2D mono and color only. The region of interest stat plugin doesn't generate arrays. I looked at that today. It just generates statistics, and it doesn't have any limitations on the input data types or dimensions. The color convert generates new arrays, again 2D mono or color only. The circular buffer plugin generates new arrays, and it doesn't have any limitations on those arrays. And then finally, the file plugin does not generate new arrays, and the limitations on the input arrays depend upon the file type. So the HDF5, NetCDF, and Nexus can handle arbitrary ND arrays. JPEG, TIFF, and Graphics Magic can only do 2D mono and color. There's some general guidelines and rules for writing a plugin. One thing I didn't even mention on here is that there's a base class that's called ND plugin driver, and all plugins will inherit from that base class. And that base class actually does a fair amount of useful stuff. So it makes it so it handles the actual callbacks, handles the logic as to whether callbacks block or don't block, implements the queue, implements the minimum time between callbacks. That's all done in the base class. And generally then what the derived classes do is they implement a process callbacks function. So this function is called with a new, with an ND array pointer each time a new array callback occurs. Your derived class should call the base class process callbacks function, which handles tasks common to all plugins, including callbacks with information about the array and so on. Not callbacks of the array itself, but callbacks with information about the array, like the number of dimensions and the data type and the timestamp, and all of that is done in that base class. But there may be times when you decide whether you really want to call that right at the beginning of your callback function, or you want to call it later for some reason. So it isn't done automatically, all those things. It is at the discretion of the callback writer, of the plugin writer. Plugins are generally going to implement one or more of the writeInt32, writeFloat64, or writeOctet functions, only if they need to act immediately on the new value of some parameter. As we saw yesterday with drivers, for many parameters, it's normally sufficient to simply have them written to the parameter library, and you don't have to handle them in the writeXXX functions. And then you just go get them from the parameter library with get integer param, get double param, get string param when you need them. However, if you do implement writeInt32, writeFloat64, or writeOctet, then those must call the base class function for the parameters that they don't handle and whose index value is less than the first parameter in that class. i.e. parameters that belong to a base class. We saw the same thing when writing drivers yesterday. You need to call the base class function. You're going to, as with drivers that we saw yesterday, you're going to need to call create param in the constructor if they have parameters beyond those that are in the ACE import driver or ND plugin driver base classes, and generally they will have some additional parameters. And then, it's very important that the plugin must never modify the ND array that they receive in the process callbacks function. And the reason for this, of course, is that it's been passed as a pointer to other plugins, and they are maybe concurrently operating on that same array since they were passed the same pointer. It also means that when you get the attributes for this plugin, remember every plugin can have its own attributes file that gets added to the attributes that you that array already has. You must not call that with the array that was passed to process callbacks, because that does modify the attribute list and hence the array that the other plugins are operating on. Generally, if you're going to add your attributes to the array, it's because you're passing the array on. You're making a new array that you're going to pass to other plugins, and so you have made a copy of it. So you first have to make the copy, then get the attributes on that copy. So there's some examples. The ROI and color convert plugin, for example, create new arrays via this ND array pool copy or ND array pool convert, which copy the attributes to the new array, and then you call get attributes to get the additional attributes that this plugin is going to add to the ones that are already attached to that copy of the array. The get attributes function is passed an attribute list. It isn't passed an array. It's passed an attribute list which is attached to that array. So the file plugin, for example, may want to, what it does, the file plugin, is to copy not the whole array, but just copy the attribute list and then add additional attributes to that, which means that it doesn't need to copy the whole array, but it does copy the attribute list and then add new attributes to that copy. Right. I mean, right now, that it isn't structured that way. We could think, in fact, I know that Michael Davidsaver has ideas about changing this to use more of the standard C library, because there are pointers, there are pointers, reference counted pointers and smart pointers in the standard C library, C++ library, that could be used. So, at some point maybe this should be refactored to use more of the stuff that comes with standard C++. But right now, the answer is no, you can't do that. But we will look. There are a couple of variants of the copy method. One of which copies everything except the data, and one copies everything including the data. So continuing on. And this is a really important point, and which is that when the plugins often are written because they're doing time-consuming operations, right? They're doing computationally intensive stuff, or file operations that are not computationally intensive but that have long delays. And it's very important that during the time-consuming operations, the plugins need to release their mutex by calling unlock. The reason for this is that when the driver calls, does the callback to the plugin to put another array in the queue, it needs to take the lock to do that. And if the plugin has constantly got the lock while it's doing time-consuming operations, it slows the driver down because it's waiting for the mutex. So you want to release that mutex when you're doing time-consuming operations. And there have been a few instances of plugins written that didn't do that, and then we observed that when they started to get busy, they were slowing down the driver, and that's all been fixed now. But obviously, when they've released the mutex, they must not be accessing, memory locations that other threads could modify during that time, or that they shouldn't be modifying things that other threads could be reading. So they should only access local variables and not class variables, including the parameter library, once they've released the lock. But that's usually not too difficult. You go and get the stuff you need out of the parameter library with the lock held, then you release the lock, then you do your computationally intensive stuff, and then when you're about to put stuff back into the parameter library, you take the lock again. So the lock is only held briefly. And then, obviously, if plugins generate new or modified arrays, they have to do callbacks generic pointer so that all the other plugins that are in the chain with them get the values of the new arrays. Okay, so that's sort of it for the overview. And what I want to do is to look in detail at a few of the existing plugins so you can sort of get an idea for how they work. And then we'll go on to the exercise where we write a new plugin from scratch. And that new plugin is that we're going to write, and we may even get to this morning because I don't know that looking at the code for the existing plugins is going to take all that long. So writing a new plugin that's going to take an input array and compute the 2D FFT of that array and convert that FFT into a power spectrum, which means when we're going from the real to a frequency domain, for example, that's a complex number. And right now, ND arrays don't support complex numbers. So we want, if we want to get it back into something that's not complex, we can do the power spectrum, meaning at each pixel we compute the absolute value of the imaginary number, which is just the square root of the real part plus the imaginary part squared. One thing I really haven't said anything about in the classes so far is the documentation for AreaDetector. And most of you probably know about this. So go back and if you just Google Epic's AreaDetector, that'll take you to this page, which is sort of the home page for AreaDetector. And it describes the stuff that is pre-2.0, and that's all in the APS Subversion repository. And the documentation's done a bit differently, and then with AreaDetector 2.0 and on, points you to GitHub, which is the source repository for it now. The documentation for AreaDetector is still installed on our web server. So this, the link, the top level documentation link here, points you to our web server. The release notes, on the other hand, used to be a single file on our server that documented the releases, the changes to everything, because it all used to be one module. Now the release notes are on GitHub. Well, they're in these MD files, which is this is an example of one. We're on GitHub here, and so for release 2.0, each module has its own release, and you just go look on GitHub for the release notes. But the main documentation, as I said, is still on our server, which is this. And this is broken down into, sort of an overview, description of all the drivers, description of all the plugins. These, the code, the HTML code behind all these links are from the individual repository documentation directories. So there's a script in the top level area detector documentation directory that goes and gets all of this documentation and puts it into this one place on our web server, and also builds all of the Doxygen documentation and puts that on our web server as well. So if we go read, here's the documentation on ND plugin driver. So this is the base class from which all the plugins are derived. So this is the stuff that's common to all plugins is described here. And there's, each of these links here are links to Doxygen documentation. So the classes are described in detail in Doxygen generated documentation. And for example, if we, let me see, follow the links here. Just see what the, I want to get to the ND array pool stuff. So this is the document. This is the Doxygen generated documentation for the ND array class here, and here's the ND array pool class here. So you'll see that these plugins, I'm sorry, this is a pointer to an ND array pool. Here's the ND array pool documentation. This one? Yeah. Okay. So here's the ND array pool Doxygen documentation. And you'll see that the plugins are often going to be using some of these methods to create a new array, but copy the information from the existing array, convert an existing array to another type. So there's a copy method here. Actually, there's only one copy method, but there's a flag that says, do you copy the data or not copy the data? There's a convert method, which we talked about briefly yesterday. There's actually two variants of that. This one here, you give it a pointer to an input array, a pointer to the address of an output array, and you give it an output data type. So that's basically a data type converter operation. This one is more general. You give it an input array, an output array, and a data type, but then you also give it an array of output dimensions. And a dimension is itself a class that describes the order of the pixels, go this way or go this way, the start point for that dimension, the binning for that dimension. So by creating this, it's actually a structure, I guess, creating this structure that describes the dimensions of the output array, it does a lot of conversion. This is basically what the region of interest plugin, that's all it has to do, is call this. Because all the operations that the ROI plugin does are handled by this, this method in the ND array pool class. It does not scale. It can get a subset of the image. It can reverse the order of the array in any dimension. It can bin in any dimension. Binning, not scaling. Yes. So and when you write code for a new plugin or a new driver, you should follow the documentation conventions that are in the existing one. There's just a little bit of stuff you have to do if you haven't used Doxygen before to be able to make it, to be able to make Doxygen generate this kind of information. You know, it's just how you format your comments. Let's Doxygen make this nice looking, you know, hyperlinked documentation here. Right. Yes, it is. Because, you know, you click classes here and you see all the classes. And if we go to, you know, look at the class hierarchy, you know, you can see, okay, from asyn port driver down, this is a useful diagram to look at, right? To understand that, you know, asyn port driver is the top level base class, and then within the area detector package, there is a class called asyn nd array driver that derives from that, which then has an AD driver base class from which all the drivers are derived, and the ND plugin driver from which all the plugins are derived. And then there's one other class here that directly derives from asyn port driver, and that happens to be, it's called Shamrock, and that happens to be a driver for a spectrometer in the Andor package. So it's not an area detector thing, it's just you know, another kind of driver that knows how to drive a spectrometer. And there's no other base, it inherits directly from asyn port driver because it doesn't deal with the asyn ND arrays. It doesn't deal with ND arrays. It uses Andor camera, yeah, yes. It's from Andor, and so if you have an Andor camera, it's likely you have the spectrometer as well. And you know, John right now is working on a driver for the Princeton instrument cameras, the PICam library. They also sell a family of spectrometers, the ones from Acton, and you know, there's a library for that. So someday it might be nice to have that library in the same, you know, in possibly even in the same module, because like when I'm running the driver I wrote to run the same cameras John is writing, I used Lightfield, and Lightfield brings the spectrometer and the detector together, so I can control both from Lightfield. But right now, if you go down to the library level, we don't have a way to control the spectrometer. And I don't know, is the image intensifier is part of the camera, right? Part of the intensifier is part of the camera, right? And then if this doesn't go a little deeper in the hierarchy, let's see if we go here. No, you have to go click on the file. So the ND plugin file is itself a base class from which all of the actual specific file writing plugins are derived. So it's nice, you know, this Doxygen stuff is very nice for seeing how the code is laid out. Okay. So let's look first at the base class. Oh, I guess it was gedit we were using, not edit. Yeah, gedit's nicer. It's not a nicer editor, but it looks nicer on the screen. Come on. Does that happen? There we go. Okay, so for the base class, these are the parameters that you've seen on all the plugins. You know, you have the port and address you're going to connect to. This is just a string that says what kind of a plugin is this, the number of dropped arrays and the queue size, the number of free queue elements, enable callbacks, block, or do they block, and minimum callback time. And in terms of its public let me see here. Yes. So it's got this protected method called process callbacks. So typically when you write a plugin, you're just implementing this protected method here in your derived class, or potentially implementing the write int32, write octet, write float64. Again, as I said, only if you need to immediately act on some of those parameters. So this is the process callbacks in the base class, which, as I said, your derived class should call. And so it does things like setting the integer param on the unique ID and the color mode and the data type. And there are epochs PVs that are connected to those parameters. So every time you get a new array, you see the new unique ID and the new timestamp and that sort of thing. So you want to call this base class method. This is the code that the driver actually calls back with the generic pointer. So it registers for callbacks into this function, and this is where it implements the stuff about the minimum callback time, and it implements whether it's a blocking or non-blocking mode callback. So if it's a blocking callback, it simply calls process callbacks. So it's calling your plugin process callbacks in the thread that called this back. If not, it increments this p array reserve increments the reference count on this array, and then does an epochs message queue send to a thread, which a thread that this has created will be then reading that message queue. And so this is the queue of you define how many elements that queue can hold. And this is the process task, which is if you have blocking callbacks, this is the thread that's running, that's just popping those arrays off the message queue and calling process callbacks, but now doing it in its own thread. And then when your process callbacks is done, it releases the array, so it decrements the reference counter. And this is the code to, if you type the name of a new port in the plugin screen, this is what will, if you're currently connected to some port, it'll disconnect, unregister for interrupts. It'll cancel your subscription to the existing plugin and generate a subscription to the new plugin, to the new driver. I'm sorry. Well, which could be a plugin. It's either a driver or a plugin. And this is the code that actually does the connection to the port, and write int32. So this is the stuff it needs to act upon immediately. And because it has implemented write int32, if you implement it, of course, you need to call this method so that it gets to do the things that this layer needs to do immediately. Same thing with octet. And this read int32 array here, this is implementing reading the array of dimensions. So remember, each of your ND arrays can be, it has a certain set of dimensions. It might be 1, 2 dimensions, or 3 dimensions, or 5 dimensions. This lets epochs get at the array of dimensions. And this is the constructor, doing the stuff we've already seen, creating parameters and setting some default values of parameters. Any questions? Okay, so let's go look at let's go look at standard arrays first, because this is one, of course, that you're always, it's almost always in use. Okay, so this is the process callbacks method for this plugin. So first thing it does is to call the base class process callbacks, gets some information about the input array that it received here, and then it's just calling array interrupt callback for all the different types of arrays that are supported. So there could be multiple clients, right? There could be multiple waveform records that are subscribed to this plugin, right? So I could have created an int8, a waveform record that has an int8 data type, and another one with an int16 data type, and they're both connected to this plugin. So we've got to not just do the callbacks for the data type that our input array happens to be, but do the callbacks for all these possible output array data types. And these are template functions. So we're passing it here a data type, and also this is an asyn structure. There's a different structure in asyn for each type of interrupt. So we're passing it those two things to this interrupt, this template function here, array interrupt callback. And it takes an epochs type and an interrupt type. And so this is general. It can handle any epochs type and any interrupt type. And basically this is a loop going over all of the clients that have been, waveform records effectively, that have been subscribed to this plugin. And for this interrupt, for this array data type. So it's doing the callbacks. Here is basically where it's calling device support and passing it this private structure for device support and the asyn user that device support passed it, and then a pointer to the data and the number of elements in the array. And it did that by calling here arrayinfo.n elements. Let me see, did that. Where did it get that? Right here. And this is calling ndArrayPool convert it's calling ndArrayPool. So we need to do the data type conversion, right? Because the input array that we've got is some data type, and this waveform record is potentially some other data type. And so instead of doing that conversion directly, we're allowing this base class to do that conversion for us. The ndArrayPool method to do the conversion for us. And then the p data is epochs type star p output p data. So this converted to whatever the output data type should be. We got a pointer to that, and that's what we pass back to the. And we also need to implement. So that's for waveform records that are I/O interrupt scanned. But we also need to support waveform records that are periodically scanned. And they're just going to come in here and call the read array function. So we also need to implement a read array function that can handle the case when there's not, and that's again a template function. We don't need to, it only takes one template argument. It doesn't need an interrupt type, it just has an epochs type. So interrupt type, right, star p interrupt equals interrupt type star p node driv private. So this is an asyn thing, right? There's a structure that is an asyn int32 interrupt. And so I've got to cast this, I've got to cast this pointer to the right type of interrupt, of the right type of structure that asyn knows about. That's not using C++. Yeah, that's why. Yep. I haven't noticed that this takes very long to compile, but you will see, I do see that NDArray takes a while to compile. And that, that does a lot of template instantiation as well. And so there's a lot that goes on under the hood. With a little bit of input code, you generate a lot of output code. Yeah. Okay, so in the read array, okay, you got to figure out, are they really asking for the data? And basically, again, we do a conversion to from whatever our type is to this output type, copy the data. They've passed us a pointer here on this read array. They've passed us a pointer, that's a size t. Where's the pointer to the out value? Yes, epochs type value. So we're copying to value from this p output. And this is really important for memory leaks, right? NDArray pool convert generates a new array, right? This output array, and we wanted that, but it's basically just a temporary, right? We're just using this as a place to get the output, the converted data type. So down here we have, whenever NDArray pool copy, convert, or allocate, give you an array, they have set the reference count to 1. And then you need to call release when you're done with it, which puts it back, well, it decrements the reference counter, and when the reference counter goes to 0, it goes back in the pool. So you need to remember to do this. And if you don't, you'll see, eventually your IOC will die because it uses all the memory in the system. You are allowed to allocate, to call NDArray pool alloc and give it the pointer to where the data is. But I don't know if you can do that with convert. Okay, so that was standard arrays. Let's look at the ROI plugin. What was the other one I was going to do? Statistics. Okay. So here's the ROI plugin, process callbacks. So this is the routine that we do. That gets called for each array. And the ROI plugin has its, well, I said it had no restrictions, but it really, in terms of the interface of being able to control what happens along each dimension, it only supports 3 dimensions. We could generalize this to support 10 dimensions, but 3 has generally been enough for the regions of interest. So this does have a scale factor, what you were asking about, Christoph. So the convert routine, the convert routine itself doesn't have a scale factor, but the ROI plugin does have a scale factor. So we call the base class method. We always keep a copy, so the read function can use it. So if this is not null, we release it and set it to be null. Get information about the array. Make sure the dimensions are valid, fix them if they're not, update any parameters that might have changed, and let's just see. Okay, so here, all this is done with the lock taken. Here we release the lock, and here's where okay, so in this case, if we're going to be doing scaling, what we need to do is convert the array to a double. So we can do everything in double, including the scaling, and then at the end convert it back to whatever data type we want, because we can't be operating, on 8-bit integers if we're going to add them up, and then they might overflow. So we've got to convert to so I convert to a floating point data type here. And then, so this converts it to a float, does the scaling, and then converts it back to the data type that we want. If you're not doing scaling, you can directly do the conversion where all you've done is change the output dimension structure. And then we're this is taking into account the special case where, if you had an RGB image and you now selected one of the colors as the region of interest, you want to set it now so your output array isn't RGB, it's mono, and so this is, setting the color mode and so on, and what the and it also getting rid of unused dimensions, because you've got a 3-dimensional array coming in, and you're going to be outputting a 2-dimensional array, so you've got to play around with what the dimensions of the output array are. And that's a right int 32. I'm trying to see what it is that needs to be done immediately here. I guess we're just taking and putting stuff into some private data. Why that couldn't be done at the time it's needed, I'd have to think about. That we needed to do it right away as opposed to doing it just in the with a get integer param later. And the constructor. So, what you can see is that the guts of the region of interest plugin are essentially all done in the ND array pool convert. Almost all of it. The only thing that's not is that scaling. Really. And then the logic of, if you changed the dimensions of the array for color stuff, setting the dimensions back to set the color mode, get rid of the unused dimensions, and so on.
Is it because I don't remember if ROI is changing the color modes or converting between the color modes or not?
No, that's a separate plugin, with the exception that if you've got an RGB image coming in and you set a region of interest that only selects the red image, the red data, then the output is not RGB anymore, it's mono, and the dimensions, instead of being 3 dimensions, there's going to only be 2 dimensions on the output data. So that's handled here. But the general conversion from one color mode to another is handled in a different plugin. It's called ND Plugin Color Convert. Right. Okay, and then let's just look at one more, which is the statistics. So let's go down and just look at the process callbacks first. Okay, so here's the callbacks. And basically, It's calling the base class, going out and figuring out which statistics do you want to compute, the basic statistics, the centroid, blah, blah, blah. And this is doing stuff for the profiles. And then if you're computing the basic statistics, remember in the basic statistics, you have the ability to do a net counts in the array. So it has to do background subtraction. And the background is allowed, it's a box that has a finite width. So it actually creates here it makes each of those boxes along the border be arrays themselves. And so it's creating those arrays because it can then call its own statistics routine to get, the average counts in that background box. So it creates its own array and calls its own statistics routine to get some information on those background regions. And then let me see where so here it's doing if compute statistics, it calls do compute statistics on that array. If it's got background, it then modifies those statistics later. It creates some additional statistics. It takes the net counts is based on the background. Okay, here, if you're computing the centroid, do compute centroid. If you're computing the profiles, do compute profiles. If you're computing the histogram, do compute histogram. And then remember, the statistics plugin has the ability to collect a time series of all of those statistics. So each time a new array comes in, it puts an additional element in a time series. So if that's running, this is where it does that. And what is this doing? It's actually making an output array and doing callbacks generic pointer on that output array. I have forgotten that it did that. So the answer is the statistics array does do callbacks on the output. Does pass the output array through. And then it saves a copy of the array, right? Because you can there's a cursor, and you can get the cursor profile on even if the array hasn't changed. So, if you've stopped acquiring, you still can move the cursor and see the row and column profile of where the cursor is. Of course, it needs a copy of the last array to be able to do that. This is where it's doing so the stuff like updating the cursor X or Y, it wants to act immediately on that. As soon as you move the cursor position, you want to get the new profile of that cursor position. So that's why the write int 32 is implemented here, and there's a write float 64. So, right, there's a centroid threshold. And so even if you're not acquiring, if you change the centroid threshold, you'll get a new value of where the centroid is. So you don't have to wait till the next image comes in. It'll recompute it on the last image. And then just go look at a couple of those functions up there. What's a good one to do? Okay, so here's the centroid calculation. So what the process callbacks called was do compute centroid. So that's this function. Now this has to go through and call a template function depending on the data type of the input array. So it's just got a case, a switch statement with the cases for each of the data types, and calls do compute centroid t, where t here means template, for just passing a template parameter, which data type is the array. So the guts of the calculation is here. So this is do compute centroid with a type, so the data is cast to whatever that epoch's type is. And so it's basically, doing centroid calculation here. And the centroid has a threshold, so you're only counting things that are above that. And it actually does it in a very efficient manner. So what it does is to calculate the average row and the average column. So it just sums up along all the rows and sums up along the columns, and then computes the centroid in one dimension of the average. And you can show that that's mathematically equivalent to doing a two-dimensional centroid, but a heck of a lot faster. Yeah. And so this is the same thing for the basic statistics. It calls this, then it calls a template function for each of the data types to compute the basic statistics. So this is just, the min, the max, mean, sigma, and so on, and then the pixel where those occur, those minimum and maximum occur. Any questions? Okay. Why don't we just plow through into the exercise for those who are interested. And so we could probably get done here before lunch if we want. Today's so on the same place that you found the previous labs. And they're on our website at, where is that? Here it is. So if we go up a level. So now there's a day 6 here, and the AreaDetector Plugin Lab PDF file is here. Very similar to yesterday. All the setup stuff is the same. So what we're going to do is write a plugin that computes a 2D FFT of the input array. And so it's going to implement 3 new parameters. So you're going to be able to, you want to control the output data type. So the input array is going to have some data type, and the FFT plugin is allowed to create an array with a different data type, including automatic, which means use the output data type is the same as the input data type. A scale factor for the power spectrum, which if your output data type is an integer, that should be useful for getting you back into the range that those integers can handle. And then an FFT direction, which sets, are you going from the spatial to the frequency domain or from the frequency domain to the spatial domain. In the teacher directory on Corvette, there's a new database, ndfft.template, that contains just these 3 records here. The source code is in AD-Core AD-App plugin source. So there are 2 new files there, ndplugin.fft.cpp and ndplugin.fft.template.cpp, just like yesterday. So the template has basically got all the code removed. The ndplugin.fft is full-fledged. I've also modified the make file in this directory, so it builds this new one, and there's a dbd file for this, and the dbd file has been modified to pick it in. So if you copy again today from the teacher directory to your student directory and do a make, you'll get an example IOC in the SIM detector IOC that has this new plugin. What I haven't modified, I've created a new ADL file, ndfft.adl, but I haven't put that as a related display in the main thing. So you have to launch MEDM for that separately. So you could launch MEDM for the SIM detector and then separately launch MEDM with a different R macro parameter here for the ndfft ADL. Start the IOC just as you have before, and then you can try building the real driver from the skeleton driver. But let's go take a look at the real plugin. So if we do gedit ndplugin fft dot star. So let's look at the header file. Header file, we've defined 3 parameter strings here: FFT scale factor, FFT data type, FFT direction. This is a float 64, and these 2 are integers. Got the 3 protected variables for holding those things. And then we've got one private function. It's a template function that takes an epochs type, and it's compute FFT. So and we got a process callbacks function here. We don't implement actually any other functions like write int 32 or write float 64. It's not necessary for this. The dbd file, of course, just has that register command. Okay, so let's go look at the process callbacks. So process callbacks is pretty simple here. You get past the array. We call the base class process callbacks. If the number of dimensions is not equal, so this is not written to be, it only handles 2-dimensional input arrays. So if the number of dimensions is not 2, it prints an error message and returns. Previous version of the array was held in memory, so we release it. And then we've just got a switch statement here on the data type of the input. So we can handle any input array data type. We just call that template function, compute FFT with the appropriate data type. And then at the end, do callbacks generic pointer and call param callbacks. The constructor is trivial. We're just creating those 3 parameters. Every plugin has this plugin type, and so we set that to be our ND plugin FFT string. That's just so that on MEDM you can, clients can see what kind of a plugin it is. And then we try to there's a base class method connect to array port. So typically the constructor is passed here the initial at least port and address to connect to. And so the constructor tries to connect to that. Those, of course, can be changed at runtime, but this does the initial connection, if it can find it. And so the only other thing we need to look at is that template function, which isn't really very complicated. So, so this is the template function with an epochs type, compute FFT. We go get some information about the input array here with this getInfo method that's implemented in NDArray. We go get the current values of the FFT direction, the scale factor, and the output data type. There's a special case output data type of -1. That's what the MBBO record defines for automatic. That's not one of the possible enums for an NDArray data type. And says, so if it's -1, it sets it to whatever the data type of the input array was. And once we've done that, that's the only thing that should be accessing any class data. So we unlock here. And now what I'm using and what's in that plugin source directory now is the code totally against license requirements for the Fourier transform function from numerical recipes. So that Fourier transform function, it's called for(n), which means it's n-dimensional. It only works on dimensions that are powers of 2. And so our output array, we want to make it be the next bigger power of 2, or if the input array is not a power of 2, make the output array be the next bigger power of 2 from the size of the input array. So this is just going through on the x size and basically compute size x here if you follow the logic. It's, if size x starts at 1, if it's less than ArrayInfo.size, multiply it by 2. So we're going up until when this exits, size x and size y will be either the size of the input array, if it was a power of 2, or the next bigger power of 2. The for(n) function wants a float array. Well, basically, you're passing it a complex array. So it wants for each element 2 floats, the real and the imaginary part. We're just going to be filling in the real part with the data we've got here. So we have to allocate a float array that's got size x, this power of 2, times size y, times 2, because the FFT for these routines is done in place, and the output is complex. So we allocate 2 times size x times size y, and then we go through here, and we're looping. And now we're going to be 0 padding if we made the output array be bigger than the input, we want to pad it with zeros. It's all been set to zeros because we did it with calc, and now we have to pad it with zeros. We got to do it in the right dimension. So we do need a 2-dimensional loop here, so we're saying the output array is equal to the start of it plus 2 times I times size x, and there's a 2 times j here. So we're basically copying the input into this temporary floating point array. Then you have to give the for(n) routine an array of dimensions. That's this LDIMs, and they need to be unsigned longs, and the number of dimensions. And then in this, I don't quite know why, but this for(n) wants not a pointer to your data and a pointer to your array, but a pointer that's one before it. Does that have something to do with how Fortran works or something? I don't know why they do it that way, but you have to pass it not FFT, but FFT minus 1 and LDIMs minus 1. And so that does the 2D FFT. You pass it which direction you want to do it in, 1 or minus 1. And so now what we're going to do is allocate an array of type ND float 32. And the dimensions are going to be the same here, size x, size y, this power of 2 thing. And then I'm I believe that their routine, with basically what the FFT direction does is control, some scaling of the output. And I think this logic is right, but I'm not sure. So we give it a scale factor, but if the direction is 1, that scale factor should be divided by the product of the 2 dimensions. I'm not absolutely sure about this. So now this was a temp array. We got a pointer to its output because we know it's float. And so now what we're doing is going through and saying in this output array, compute the absolute value. So FFT 2 times I, so that's the real part, and 2 times I plus 1, the imaginary part. Take the square root of the square of those, and then multiply by the scale factor, and that's what we put in our output array. That was a float array, but now we want to convert that to whatever the output data type is. So we use the ND array pool convert. Now we free this thing that we callocked, and we release this temp that we generated here, that we allocated. And then because we didn't do this, we didn't basically take the input to the output with a copy or a convert, it didn't get any of the metadata. And we should really have another way in the base class of doing that, of basically saying copy. There is a copy that doesn't copy the data, but it does copy the dimensions. And that wouldn't be right, because the dimensions here might have changed because of the power of 2 thing. So I had to manually copy this metadata, the unique ID, the timestamps, and the attribute list. And then now that we're done with all of this, take the lock and return. So that's it. So we could see how it works. And unfortunately, graphically, you can see numerically sort of how it's working, but graphically, I can't see images. It's like, I think that's because the DC offset of the images is like huge, and all the interesting frequency stuff is tiny, and I haven't been able to get it to scale to be able to see an interesting looking image. But we can see it with the statistics plugin, what's going on. So let me start the IOC. Okay, so the IOC is running, and this FFT plugin is in the IOC. And I'm going to need to start 2 instances of MEDM here. So I want to go to teacher, AreaDetector, AD core, AD app, op ADL, MEDM minus X minus macro P equals sim underscore 1, R equals cam1 colon, sorry, I should have made a script to do this. That's simdetector.adl. And then we want to do another MEDM, which is where the R is changed to FFT1. Okay, so I have the simulation here right now is generating, let's go and generate, unsigned int 8 data. And I've got it running at 5 hertz. And this is the new plugin, and this is the MEDM screen I made for it. It's basically, this is just the one from the base class. So this is a is like an included display in MEDM. So you get all of this in MEDM. This is all the stuff that comes from the ND plugin driver base class. These are just the 3 new records that have been added for this plugin down here. So I can set the data type, the scale factor, and the FFT direction. So this is going to get its data from Sim1. Let's enable it. Okay, so it's getting an input array that's 10. This is doing 1024 by 1024. This didn't need to change the output dimensions because, this is telling you the dimensions of the input, actually, and that it's U8 and mono. Let's go also open the statistics plugin here. And it's set up to get its data from FFT1. And it is 1024 by 1024. And this was set to automatic, so its data type is also uint8. And you can see that it's got, the maximum, it's got the minimum pixel is 0, the maximum is 127, and the total is 350 something. So it looks like the FFT is calculating something. If we change this instead to output a float 32 array, so now the input to the statistics plugin changed to float 32, and now these values changed because they were bigger than 255. So when they were being assigned to 255, they were wrapping around, right? So they're going up to a few thousand here. We could change our scale factor to 10. And, oops, didn't take. So now our 100. So now our maximum values are up in the tens of thousands. If we change this, so it's generating arrays that are 900 by 900. That's not a power of 2. So the input array to the FFT is 900 by 900, but you see the output here is still 1024 by 1024 because it did that rounding up to the next power of 2. We could make this so that the output is, an int 32. You can change it so it's doing the FFT in the other direction. Then the magnitude of the numbers changes dramatically. I've probably got the scale factor wrong in the code there. That I should be doing the scaling in the case when it's -1, not when it's 1. But I'm not certain that this FFT data is right. One of the things that makes me, let's make this be float 32. So it should just be passing the sort of the raw, what it really calculated for the FFT. And when I look at the, at the average X profile here. Oh, now that doesn't look too bad. I was seeing that. And let's see what the cursor, there's something there that's not all zeros in here, which is what I was seeing before. Let me do like cursor X. So that's an individual profile. Oh, because before I was seeing that it looked like all the pixels except right at the ends were 0. So maybe we would see something if we looked at this with ImageJ now. Let's give that a try. Let's make this a little smaller. Yeah, we still have non-zero values in the array. That's good. Okay. And now the outputs should be 512 by 512. Yep. Okay. Just go. So this is sim1, image1. Make sure that plugin is enabled. Yep. And it's getting, oh, it's getting 512 by 512 float. And I changed the startup script for the IOC so that the field type of value, the FTVL of the waveform record is float. And so that image J is now getting float arrays. And still, okay, so if we look at those profiles, they're down around, that's the average. Let's look at a specific profile, because that could be averaging some huge number. Okay, so there's a few pixels here with counts that are up around 1,000, and then a bunch that are down just probably around 10 or something. So if I set this, to have a maximum displayed value, let me just do that like 20. Okay. So we're seeing something. I have no idea if that's right. So ndplugin file.h. So this defines the base class, ndplugin file, which derives from ndplugin driver. And then this defines 4 virtual functions: open file, read file, write file, and close file. And the open file is passed a file name, a bit mask that says, are you opening it in file mode read, write, or append? And there's also a bit multiple if the file is to be opened to write or read multiple ND arrays in a single file. And then you're passed a pointer to an ND array. That array, you're not to pay any attention to the data, but you use basically the metadata in that array to figure out whatever it is you need to know about how to, when you open that file. Because if we're going to be, the dimensions, the data type, all the attributes, you look at that array to figure out how to create the file, but you don't actually write that data to it. then read file has never been implemented. That's a future thing where you could give it a file and then it would read an array and return an ND array. So that this would be a file drive, it would be a driver, or it would be a plugin that's a source of arrays. Someday we should get around to implementing that. Write file, you're just passed an array and you take the data from this array and write it to the file. And it could be that you're appending to a file that's going to have multiple arrays. And then finally there's close file, that you're just, self-explanatory, you close the file. And there's a public data flag here which your derived method sets to 0 or 1 to indicate whether your file format supports writing multiple arrays or not. And yeah, I mean, that's about it for what your derived class needs to do. If remember this, there's this lazy open flag that the user can choose, but all that really does is delay calling open file until the first array arrives after you've started to stream the data. If you don't use lazy file, it takes the last array that arrived before you started to stream the data and passes that to open file. If you set lazy open, it caches the fact that you'd like to call open file, but doesn't actually call it until the first real data array arrives. That has the advantage that you don't have to follow the rule that the previous array that you collect, the last array that you got, has to be the same structure, data type, and everything as the data you're going to be streaming. But the disadvantage is because it's slowed it, file opening, file creation can be slow. If you don't start doing that until the data begins to stream, you could fall behind. You're more likely to fall behind. But that's transparent to whoever writes the driver, the file writer here. And then, of course, you can do additional things like the HDF file writer and the Nexus file writer implement write octet, and so that to get the name of an XML file that they use to control how the file is laid out. And the base class, so let's look at the C++ file. It has quite a bit of stuff in it. Well, it can now create, this is something that's been added recently, and I haven't actually even tested it, but you should know about it. So it now has the ability to, if you give it the name of a directory that doesn't exist, for your path, it can optionally create it subject to these rules. So there's a new EPIX-PV that corresponds to this. So if this value is 0, then it's not allowed, and that's the default. It's not allowed to create directories at all. If it's 1, then there's no limit on how many directory levels deep it's allowed to go. If it's 2, what does that say? Assume 1 directory below the root directory exists. Okay. And -1, -2. And I think these can go up to bigger values than this. So it basically controls how many additional levels of directory you're allowed to create. It's allowed to create. So if you get a typo, way early on in your path, it protects you against creating something that's many levels deep. So this is a base method for opening a file. It's ultimately going to call your derived method. That's this one. And similarly for closing a file and for reading a file, writing a file. This is where a lot of complexity comes in because it's, you know, are you in single mode? Are you in capture mode? If your driver, does your file derived class support multiple arrays? Yes or no? You know, it gets pretty complicated because, you know, in one case it's creating a whole bunch of individual files, so it has to call open file many times. Otherwise, if it supports multiple arrays, it just calls open file once and then just calls write again and again and again. Then there's the logic to implement deleting the original driver file in the case where that's enabled. Then it's got this capture buffer. Now, a lot of this is probably going to go away, as I said, because I'd like to simplify it to the point where we don't have single capture stream, that there's just how many files, how many arrays do you want to save, and how many arrays do you want to put in each file. That you would just be those two things and get rid of the different modes and the auto save yes or no. But that probably requires, you know, a major release of AD core because it'll break things.